All right, here we go. We're jumping into the point of inflection. So the point of inflection is a point on the graph of a function where the concavity changes. So you go from concave down to concave up, or concave up to concave down. That sounds a little bit like where we go from positive slope to negative slope and negative to positive. It's because it is very much related. In function speak, the point of inflection occurs when, well, concavity is all about the second derivative, right? And when we're concave up, the second derivative is positive. We're concave down, the second derivative is negative. So it's where f double prime changes signs. So the sign of f double prime changing signs determines a change in concavity. Let's see this on the graph of f right now. At what x value does the point of inflection occur on the graph below? Well, we want to know where the concavity changes. So we're concave up, concave up, concave up, concave up, concave, right about there. That's the point of inflection, and that's because that is where we change from concave up to concave down. The slopes stop becoming more positive and start becoming less positive and then more negative. That's it. That's the point of inflection. That's sweet. So it would be at x equals b in this case. All right, so on to actual problems with numbers. Let's rock. Find the points of inflection in the following functions. Justify your answers. So I'm going to do the justification once, right, on this first problem. And I'm going to actually justify it first. So I'll say a point of inflection occurs where f double prime changes signs. So point of inflection, no abbreviations, of course, on major tests, right? Point of inflection occurs where, let's see, y double prime changes signs. That's it. And then you go from there, right? That would be your justification. And this occurs at, would be another way of concluding it. Now we want the points of inflection, which means we need the x value and the y value. So we need the second derivative. Let's go d1, the derivative, which would be 3x squared minus a 6x. It's nice. It's really nice, right? You got this. Let's keep going. Y double prime is equal to the derivative of the first derivative. Now you see why we learned how to do, right, second derivatives earlier. That would be 6x minus 6. Okay, very, very nice. So we set this equal to 0 because that's the only place where a function can change signs, that or where it doesn't exist, but this exists everywhere. So 6x minus 6 equals 0 when x is equal to 1. Add 6 to both sides, divide by 6. So this is your possible point of inflection. We have to test it. Just like we tested the first derivative to see where relative maxes and mins could occur, we have to test the second derivative to see where points of inflection, concavity changes could occur. So I'm going to put 1 right here. I'm going to do a test point, remember, into the second derivative. We care about the sign of the second derivative now. So I'll plug in 0. When we plug that in, we get a negative number. And so we're concave down here. I'll just put CC down. And that's on y that we're talking about. And then above 1, 42,000. Times 6 minus 6 is positive. It's a big number. So we're concave up on y. All right, so the curve is going to go from concave down to concave up, meaning there's a point of inflection at x equals 1. So I'll say, therefore, POI, or POI, yeah, POI, as I like to say it, at x equal to 1. But we need the point. So to get the point, the y value is needed. We'll plug that into the original curve. So I'm going to plug y into it. That's not y times 1, that's y of 1. That's 1 cubed minus 3 times 1 squared. And that simplifies out to being 1 minus 3 or negative 2. So the point of inflection is at 1 comma negative 2. And again, we justify it by saying a point of inflection occurs where y double prime changes signs. This happens at x equals 1. So the point of inflection is at 1 comma negative 2. It's a beautiful thing, right? I think so. Definitely Stoke worthy, or worthy of Stoke. F of x equals cosine x. We're going to find the POI on this interval, because cosine's got a lot of points of inflection. I mean, imagine it's just a wave function, right? Woo, again and again and again. So we're just going to look only from 0 to 2 pi, because that function's going to go like that, roughly, right? So we're going to have a couple of POIs, though. Let's figure out where they are. We need the second derivative. Let's go. F prime of x is equal to minus sine x. We don't stop at the first derivative because we're aiming for concavity. So we go right to the second derivative, blow right through that train stop. The derivative of sine is cosine, so the derivative of minus sine is minus cosine. And again, we're going to set that equal to 0 on this interval, because we want to figure out where cosine could change signs, or minus cosine could change signs. Well, where is it 0? Well, if you look at your unit circle, cosine is 0 where the x values are 0, and that's going to be here at pi over 2. and they're at 3 pi over 2. Okay, those are possible points of inflection. We don't have special names for them. They're possible points of inflection. So we're going to go from 0 on a number line to 2 pi, and we're going to kind of cut this up into pieces. Pi over 2 we'll consider, and a 3 pi over 2. There we go. You ready? Of course you are. Let's do it. So in terms of our signs, I'm going to plug in a number between 0 and pi over 2 into our second derivative, pi over 6. Well, cosine of pi over 6 is a positive root 3 over 2. That makes it negative. So in terms of this is f double prime, in terms of f, we're now concave down. From pi over 2 to 3 pi over 2, a really nice number to plug in would be pi. And minus cosine of pi, well, cosine of pi is negative 1. This makes a positive 1, so we're positive. So we're now concave up on that interval, or ERP, if you will. And then 3 pi over 2 to 2 pi, it doesn't matter. Any value in this quadrant right here in the unit circle. So cosine of 11 pi over 6. That'll give us a positive root 3 over 2. That'll make it negative. So now we're concave down. Not bad. All right, so we need to find the points of inflection. Again, I'd make the statement, a point of inflection occurs where the second derivative changes from positive to negative or negative to positive, and this occurs at, and then I'd list out my values. So we're going to have points of inflection at pi over 2. The second derivative changes signs there. And at 3 pi over 2, because the second derivative changes from concave up to concave down there. And sure enough, check out the graph. Concave down to concave up to concave down again. There you have it. That's sweet. It all shows up in the graph. All of a sudden, the graphs start making sense on a new level. Oh, it's magical. All right, so we take those values. We need the y values, so we're going to plug them into f. So I've got f of pi over 2, not such a bad number. Cosine of pi over 2 is 0. Oh, that's nice. And f of 3 pi over the deuce, well, cosine of 3 pi over 2 is also 0. So we have 2 points of inflection. One that occurs at pi over 2, comma 0, and the other at 3 pi over 2, comma 0. And that's it. That's all this problem wrote. So points of inflection occur where f double prime change signs. Now think about that. That makes sense. It's like we're doing the first derivative test of the first derivative, right? You're figuring out where the first derivative slopes are changing signs by taking the second derivative and figuring out where those signs change. You might need to listen to that a couple times because there's a lot now. Where the second derivative changes signs, that's your point of inflection. Check it out. Rewatch it if you need to. It's sweet.